The goal of this experiment was to construct a magnetic train by coiling copper wire into a solenoid and inserting a battery with magnets attached to both ends. When placed inside the coil, the battery unexpectedly propelled itself forward, consistently moving in the direction of its negative terminal. Initially, this behavior was confusing, but further analysis revealed that the motion was driven by the Lorentz force and the interaction between the magnetic fields of the solenoid and the permanent magnets. The key to the system's operation was the completion of an electric circuit. The magnets, made of conductive metal, connected to the battery terminals to the copper wire, allowing a current to flow. As electrons moved from the negative to the positive terminal, they generated a magnetic field around the coil, following the right-hand rule, where the thumb points in the direction of conventional current and the curled fingers indicate the field's orientation. This solenoid was uniform along the coil's center, but diverged at the ends, meaning the field lines spread outwards. The two magnets were carefully aligned with identical poles facing the battery. Example would be both south poles were positioned precisely where the field lines began to diverge. At these points, the magnetic interaction produced a net force. The front magnet, in direction of motion, was repelled by the solenoid's like pole, while the rear magnet was attached by the opposite pole. This push-pull effect generated the continuous thrust. The motion was self-sustaining because as the battery moved, the magnetic field shifted with it, maintaining the diverged regions as the magnet's locations. Interestingly, the direction of motion depended entirely on the magnet's orientation. If both magnets were flipped, example being north poles facing the battery, the train would move towards the positive terminal instead. Reversing only one magnet would cancel out the forces, preventing motion altogether.